Very good morning to all of you. Now, today we are going to have some words about group theory. 2 or 3 questions in every competitive exam containing this chapter in syllabus. You can expect 2 to 3 questions. So, what is set? First of all, we have studied set in our 12th mathematics, but here we will revise the concept. So what is set? Set is set of distinct elements which can be combined together according to certain mathematical axioms. So there are certain mathematical axioms under which a set can be defined. First of all, the elements must be distinct and they must obey the mathematical condition defined for them. The process of combination of elements of a group through a mathematical axiom called group axiom. What is group axiom? The combination of elements of a group through a mathematical condition this is a mathematical condition because of which a mathematical equation said to be true for defining set is called axioms. It must satisfy the following properties. What is the first property? To become a set, closure axiom or closure property. If we have a group and it is an element, distinct element A, B and C, no element will repeat itself. Okay, if A is element G and B is element of G, then operation, it can be multiplication, addition, subtraction, maybe in other operation also, like in we use in matrix. So if both elements are from the group G, then their resultant after applying the operation must be element of the same group. Then we will say that the set is showing closure axioms property or closure property. What is associativity? Again, we have a group with distinct elements, and like this, if this is the general statement, okay, if we are applying the operation B and C and then we are applying on A, then it must give the same result as we applied first A and B then C. It is associativity, Now, identity elements, in Hindi we called it tasmak. If A is element of G and I is element of G, then it should be follow this condition. Means A operation I must be equal to I operation A and must be equal to the element A. Then we will say there is exist identity element of the set of the group. For a group of certain element for algebraic addition, axiom I equal to 0. We know for algebraic addition the I is 0. For mathematical multiplication it is I equal to 1. Now the existence of inverse. For all elements of G, inverse will exist if it follows this condition. Okay. So first is closure property. Second is associativity. Second, identity element existence. Third, inverse existence. These 4 properties must be followed by the elements of the group. Then only we can say the set of elements is a group, or else it will not be called as group. It only called as set. Now example, set of integers. We know what is integers, plus minus 0 to both sides. Is it a group for algebraic addition? Let's check. First, closure property. If we take 2 elements from the group G, then the resultant element also is the element of group G. That is, for all element of A and B G, the operation of addition on those elements and resultant of after that operation is also an element of the same group G. So it is following the closure property. Same with associativity, you can see. Now identity element, we know for mathematical algebraic addition the identity element is 0. How it is following identity element condition? Because 0 plus A and A plus 0 will give you same result equal to A for an element of G. Is there exist of inverse? Yes, we know for mathematical or algebraic addition the inverse element is minus A, and for multiplication it is 1 by A. Okay. Now in general, group multiplication is not commutative. We know that a commutative group. The multiplication is not commutative, okay? And we know if the group is commutative, then we say it is an abelian group. And the total number of elements is the order of the group. If n is the order of the group and it is finite, then group is finite group, or else it is infinite group. Very simple, we know this. A group consists of a single element. If there is only one element, single element in the group, and its powers is called cyclic group. What is the order? Order is n simply. If n is the smallest positive integer for which a n equal to I, smallest positive integer, remember, then it is n is called as order of cyclic group, and it is also called as order of the element a. Suppose we have a group now for multiplication 1 iota minus iota and minus 1. So it is following, is it following closure property? Check. 1 multiplied with iota is iota, which is also element of G. So no matter if you take these two elements, minus iota minus 1, so it will be plus iota, again element of group. So for all a be element of G, a cross B element of G, so it is showing closure property. It is also showing associative property also. Now for multiplication we know identity element exists, that is 1, means 1 cross 1 cross iota equal to iota cross 1 equal to 1. And for inverse we know for multiplication inverse is 1. Why it is? Because when you multiply iota cross minus iota, what is giving? Plus 1. Okay, and when you multiply minus 1 and minus 1, it will again give you plus 1. So for inverse is 1. Order, number of elements of the group, order is 4. Is it cyclic? Yes, because you can write iota square minus 1, iota cube minus iota 4 plus 1. So G is cyclic group, order 4. Now if I is this, A is this, B is this, and C is this, simplistic identity matrix. So a group formed by these matrices is GIABC, order of 4, and axiom is mathematical multiplication. Let's check. Identity element exists? Yes, I exist. Associative following, closure is following, inverse of A is C, inverse of A is C, we can check it. Inverse of B is B. How we can check it? Multiply it. Multiply A with C, A with C. So what will we have? 0 and minus 1, 0 and 1, sorry, 0 1 and plus 1 and 0. So again we are having an transpose of this matrix. Okay, so inverse will be A of C and B is B. You know inverse, adjoint A divided by mod of A. So we can draw a table here, IABC, to multiply IABC, you know, AIA, AAB, and ABC and ACI. So multiplying A with C, it is giving identity element. It is the property of inverse. So it is inverse of A is C and inverse of C is A. Same BIB, BAC, BBI. B inverse of B is B, and BC is A. Similarly, AC inverse, a set of all n cross n unitary matrices A degree is I, it is forming a group under matrix multiplication. So set of unitary matrices form a group. Pauli matrices of I2 cross T is also a group. Symmetric transformation So just remember these examples. It can be asked in statement form in MCQ type questions. A set of all symmetric transformation which leaves physical system invariant forms a group. Now what is a group? The subset of element G, है ना? It is called, what is subset? Subset is simply some or one element of the group G forms a group under same multiplication as followed by G itself is called subgroup H of G. In example, we will get more clear idea about this. For every group, there are two trivial subgroups. Every group has a two subgroups. What are those two subgroups? The identity element and the group itself. Okay, these two are always subgroup of G because it follows all the closure, associativity, inverse and identity. All four properties are satisfied with this. Here 1 and minus 1 also will be subgroup of G and identity also subgroup of G. Now whole even numbers positive, negative and 0 forms a subgroup of H of a group G of whole integers numbers under addition. Now look at this. I equal to A. So H equal to IB is the subgroup of G formed by this all I, A, B, C. What is G? G is here. I have written it here. G is I, A, B, C and subgroup is I, B. Now conjugate element. A group has two elements A and X such that X A inverse element is known as conjugate of element A. Very important, remember. Conjugate X A inverse X A X inverse element of G. If this condition is satisfied, then conjugate element will be called. Order of a finite main group G must be integral multiplier of the order of any group of its subgroup. What does it mean? That we have any finite group, that is G, and it has a integral multiple of order of any its subgroup H. What is saying? Look at this. It has order of 4 and its subgroup is this. So order of H will be always equal to or less than order of G. Means subgroup can never have order greater than its original group. Subgroup will always have order within integral multiplication of order of its main group. This is the whole statement. Now isomorphism. What is isomorphism? Suppose these are the group of order and G and this is G prime. So if there is one-to-one correspondence, between the elements of G and G bar, like this, Gi G bar, such that this operation Gi operation over Gk is giving the same result at Gi operation Gj equal to Gk prime. Such groups are called isomorphism to each other. Means you are applying any operation within the two element of the group, suppose 1 and 2, and if you apply the same operation with prime elements G1 bar and G2 bar, both will give the same result. In this condition, we say that group is following isomorphism. Now similarly, group G is a cyclic group with this. So these both are showing isomorphism. How? Why? Suppose we take element 1, we take element A4, which is the identity element, so it will again give 1. Suppose this is giving iota and here A element is giving the same as iota value. Now it's minus iota, so when you do A cube equal to A square dot A square dot A will be equal to minus iota. So it is showing one-to-one correspondence. When you solve cyclic powers of this group, it will have same result as this group. Now homomorphism. If there is a group multiplication correspondence between two groups, not necessarily one-to-one, such that J equal to Gk implies equal to Gk, then two said to be homomorphic to each other. What does it mean? It means that mapping of several elements of the group G is one element of G prime such that multiplication is greater. Let's understand by example. Suppose we have these two, and we showed that how it is following isomorphism. Now from homomorphism, it is 1 and minus 1 is I, and iota and minus iota is A. So 1 dot iota is iota, and minus 1 dot minus iota is equal to I. So you can say that for mathematical multiplication it is preserved, means both are giving the same result. So it is homomorphism, isomism, but both are followed. So you can understand by Venn diagram also. Homomorphism is a big and isomorphism is a subset of that homomorphism. So if homomorphism is there, isomorphism will be also followed. But if isomorphism is the following, then not necessarily that homomorphism will be followed by the set of those groups. Okay, so see, in simplest way we can understand that mapping of all the elements of G to the identity elements of phi. If you have two group and the elements of the main group are identical elements of the phi, then we will say it's a trivial homomorphism. Now 3D rotational groups, or ON and SON. It is the orthogonal order of a group of order n. It is a special orthogonal group of order n. A group denoted by SO3 is formed by set of whole rotation in 3D space. The property of this group leaves the length of a vector gamma xyz invariant after transformation. Okay. So here 3 is showing the 3D space. And what is the property? Property is the length of the vector is invariant. Okay. So after applying the operation, if the length of the vector is invariant, then we will say it is SO3, it is a 3D group of rotation, 3D space rotation group, and it is a special orthogonal group of order here. So O is stands for orthogonal, S for special. Just remember it. In general, the group of all orthogonal transformation in 3D space which leaves the length of the vector gamma xy is denoted by O3. SO3 is a group of O3. So you can say if a group is followed by O3 and SO3 will be its subgroup. Okay. And what is the condition? Length must remain invariant under any rotational transformation. Now again, suppose we have orthogonal transformation and it is a square equal to mod of determinant of a square equal to 1 and a is plus minus 1. So if mod of a determinant of a is 1, then if it is pure rotational group and it is element of SO3, a special orthogonal group of order 3 are element of this mod of a equal to 1. If determinant is minus 1, then it is either pure inversion or combination of inversion plus rotation. So in this case, when this is satisfied, this condition was satisfied, we say it's pure rotational. What will you say? It's pure rotational. And SO3 type means a special orthogonal group of order 3 here. But if mod of A is minus 1, then it's either pure inversion or combination of inversion or rotation. Okay. Now special unitary groups of 2 and 3. Now unitary group in an nth dimensional vector space, a set of all unitary transformations forms a group. Unitary group is called unitary group. Just simply set of all unitary transformations. And its nature, remember this, its nature is isomorphic to the group of all unitary matrices. Under matrix multiplication operation also remember, under which operation is showing isomorphism, unitary group. Simply if 2 is in order of 2 cross 2 matrices, determinant will be plus 1, always plus 1. And we know a special group is the subgroup of main group, unitary matrices. Now generators of unitary groups, this is very important, remember this. So a special unitary matrix is there, group of special unitary matrices. So generator of S1 equal to n square minus 1, very important MCQ type, not in your university exam but MCQ type. So generators of SU2 equal to 2 square minus 1 equal to 3, and SU3 is n square minus 1, 3 square minus equal to 8, and every cyclic group is abelian. Thank you for now, see you later.